Hello and welcome to this video titled IP version 4 header fields. In this video we're going to talk about, just like the title slide refers to, we're going to look at the header that IPv4 adds to the front of every packet, and we're going to inspect all the different fields in that IPv4 header to determine what the field is and what its purpose is. So let's just go right into it. So when data is passed down from TCP or UDP or something else and is passed down to the networking layer, the OSI model, if IP version 4 lives there, then IPv4 is going to take everything that was passed down to it and add its own unique header to the front of that data. That header is what turns this entire thing into what we call an IP packet. That header contains some address fields as well as a whole bunch of other things that allow that packet to be routed through a routed network. So let's take a look at that header and inspect each one of those fields. So this box here is going to represent the header. So starting with the version field. So the version field is either going to be the number 4 or the number 6. So IP version 4 has been around for decades. There's more and more IP version 6 being seen these days, but you'll typically see the number 4 right here. Now, as I go through this, I'm also going to go back and forth with a Wireshark sniffer trace so we can actually see this in real life. So let's go right to that right now. So in the event that you're not familiar with this tool is called Wireshark, and it's a free tool that you can download. Just go to www.wireshark.org and you can download it. And when you start up Wireshark, it's going to ask you which of the network interface cards on your laptop or PC you want to use to capture information. So in my case, I use my Wi-Fi NIC card, and it captures every single frame, whether it's carrying an IP packet or not, that's captured across the Wi-Fi. So here we see a whole bunch of stuff that has IP packets. So for example, if we click on any one of these, here we see right there, there is our version field right there. And we can see that in binary, it does indeed have the number 4. So this is IP version 4. All right. Actually, while we're just looking at this, let's just go through the sniffer trace and look at all the other fields here, and then we won't really need to use the slide for anything. So the next thing is the header length, which tells the receiver of this packet where the IP header ends and the next header, like the TCP or UDP header, begins. Now you might be wondering, well, why do we even need this field? I mean, isn't the IP header exactly the same size? Well, most of the time it is. Most of the time it is. But actually, to explain that, let me go back to the slide for a minute and show you something. So if we go through all the fields here, so these are all the standard fields in an IP version 4 header. And in every single IP version 4 packet, you will see every single one of these fields. But there is one field that may or may not be here, which is the IP options field. So we're not in this video, because it's sort of an introduction to IPv4. I'm not going to go into options and what they are and all the different options you may see, but I will tell you this. 99% of all IP packets, if not more, do not have an options. So the options field is very rare that you would ever see it. As a matter of fact, most of the time if there is an options field in there, it means somebody's trying to do something bad. They're trying to sneak around and do something they're not supposed to be doing, because the vast majority of IP packets do not have an options field. But because it could be there, and if it is there, it's a variable sized field. It could have one option in it, it could have more than one option in it. There's all sorts of IP options. That means that the IP header itself is variable in size, because the options field may or may not be there. So the receiver has to know, okay, where's the IP header end? Is there an options field or not? And so that's why we have the IP header length, which explicitly tells us how big the header is. By the way, notice here, you might be saying, but Keith, something looks kind of weird about this, because this field in binary only is the number 5. The 4-bit and the 1-bit are turned on, and yet it's decoding to being 20 bytes. And yes, the standard IPv4 header you're going to see 99% of the time is 20 bytes in size. So why does it say 5 and it says 20 bytes? Well, here's the reason. Notice this field, the IP header length field, is very small. It's only a 4-bit field. Each one of these bits does not represent a byte. As a matter of fact, what this represents is how many 32-bit words are in the header. A 32-bit word. So, in other words, if there was just the number 1 here, which you'll never see, then that would mean that the IP header is 32 bits. It's a 32-bit word. Now, we know that a 32-bit word is actually 4 bytes, right? Because each byte is 8 bits long. So that means if I have the number 1 here, if I have one 32-bit word, that actually translates to 4 bytes. But in this case, I've got 5 32-bit words. Now remember, a 32-bit word is 4 bytes long, so 5 times 4 bytes, this is my 32-bit word right here. That gives me my value of 20 bytes, which is indeed the size of your typical IP version 4 header. Now the next field, depending on the document you're reading or anything, here in Wireshark, it translates to the differentiated services field. A lot of times you'll see that also referenced as the TOS or type of service field. This represents the relative priority of the packet as opposed to other packets that might be seen. By default, whenever data leaves your laptop, by default, if we open this up here a little bit, it's all zeros. It's all zeros. And this is the lowest priority of packet you could possibly have, all zeros. Now, if this packet was coming from an IP phone or something like that, it would have a non-zero field. It would have some number in there that's not zero. And the higher the number, the more important, the higher the priority of this packet. So in computer networks that have something called quality of service turned on, where they can differentiate between packets based on this field, they can treat packets differently if they have a higher or lower value. So this gives the priority of the packet. Once again, that's called the type of service or TOS field, or sometimes it's called the differentiated services field. Then we have the total length. Okay, now this is the total length of the entire IP packet, the header and everything that's behind it as well. Then we have an identification. So what this is just a random number that was given to this specific packet. So when my laptop is creating IP packets, whether it's 5 packets per second or 5,000 packets per second, every single one of them will have a unique identification number. And that number doesn't mean a lot unless the packet goes through something called fragmentation. And I'll circle back to that for just a second. So for that reason, I'm going to ignore the flags field for just a minute. We'll come back to that, because flags and identification are interlinked, they're tied together. Time to live. Okay, so when an application, let's just say an application on your laptop or PC, creates a packet to begin with, whatever it is, a web browsing packet, telnet, whatever it is, that application and whatever the software is that is running that application will populate this time to live field with some non-zero number. Now, you as a human being, you have no control over this number. You have no idea what it's going to pick. Whoever created the software in the first place, they had to decide what they want to use as a default time to live. Now, what does it do? Well, think of that word, time to live. How long can this packet be alive? Well, what does that mean exactly? Well, we're going to put some non-default number in here. Like you can see, this one had a pretty big number, 255. This field, if we go over here, is only 8 bits long, so that's the maximum number that could be in there is 255. And the way this is interpreted is, if this packet left my laptop, left my PC, the very first router it hits, which is my default gateway, as it takes that packet, we'll see the time to live and it will decrement it or reduce it by 1. So if this was leaving my PC right now with a time to live of 255, as it went through my default gateway and popped out the other side, it would have a time to live of 254. So the way you can interpret this is, how many routers can this packet hop through before its time to live is over? Now, even to send a packet all the way around the world would not take 255 routers. You could actually get a packet all the way around the world and back with far less than this. But let's say hypothetically this packet reached router number 255. Okay, or maybe router 256, somewhere around there. Basically what's going to happen is eventually this time to live is going to reduce and reduce and reduce, and eventually there's going to be some router out there that receives this packet in, and when it comes in, the time to live will be 1. Now that router will say, okay, I need to decrement it. The router will decrement it to 0. Okay, at that point, after the time to live has been decremented to 0, that means this packet has to be killed. Its time to live is over, and the router will throw it away. So the only time that would actually happen is if a packet entered what's called a routing loop. If the packet entered a network where there was something wrong in the network and the packet was just circling among routers, never actually reaching its destination at all, just bouncing back between maybe the same 2 routers or a circle of routers, in that situation, this field is very useful because it would prevent the packet from circling forever. Eventually, some router would get the packet with a TTL of 1, it would decrement it to 0, throw the packet away, and now the packet's lifetime would be finished. So that's what the time to live is used for. Right after the time to live field is a protocol field. And this will be populated with some standard registered number that tells the receiver what protocol is this IP packet carrying. Like we can see here, protocol number 17 is reserved for UDP. So this tells the receiver, hey, this IP packet that you've got, start up your UDP process because you're going to have to redirect. After you strip off the IP header, what's going to be next is a UDP header. And there are many, many numbers that can go into that field. For example, ICMP is number 1. Protocol number 1 is ICMP when you're pinging something. Protocol number 2 is IGMP for when you're doing multicasting. And there's lots of other protocols that could be in here. Then we have the header checksum. And what this is if my laptop created this IP header to begin with, then what my laptop would do is after creating the header, it would run all the bits of all these fields, the total length, flags, protocol, all those bits through a formula, and that formula would spit out some number like 04639 as the number. Now, if I gave this packet to you, let's say you are the destination, guess what you're going to do? You're going to take the exact same fields in the IP header, run them through the exact same formula, and hopefully you will also get 0x4639, which tells you that nothing was changed or modified in this packet. This packet has integrity. Now, if you got this packet and you ran the header through the same formula, but you got something like 0xA123, now you'd say, uh-oh, okay, some of the bits somewhere in this header are different than what they were when they popped out of the source. There's no way to tell what changed or where it changed. You can't correct it or fix it. All you would know at that point is, I can't trust this packet because the header somehow got modified in transit. So that would be an error, and you wouldn't want to see that. After that, we have the source address of where the packet came from and the destination address of where it's going to. And you can see in this particular packet, there's no options field. That's it. That's the end of the IPv4 header. Now let's circle back around for just a moment because I skipped flags and identification. So let's talk about that for a second. Now, let's just assume that this packet is being created by my laptop or my PC. My laptop or PC is connected to some sort of network. Like in this case, I'm connected to a Wi-Fi network. And the rules of that particular kind of network say that when data is put on that network, it can only be so big and then it has to stop. We call that the maximum transmission unit, the MTU. So on most Ethernet networks, like if I was connected to a wired Ethernet network, the typical MTU is 1518 bytes as the maximum transmission unit. So, which equals, because I've done this math often enough, I think that's about 9,600 bits. Somewhere around there. It's very close to that. If you do 1518 times 8, you'll come up with something really close to that number. So the exact number is irrelevant. What's relevant here is that my laptop, if I was connected to a wired Ethernet cable and I was to start putting bits on that cable, put an Ethernet frame on that cable, the maximum size of that Ethernet frame is 9,600 bits. Then I have to let it go. I have to be quiet, give somebody else a chance to speak on the cable before I put my next frame on the cable. Now the Ethernet frame doesn't have to be 9,600 bits. It's completely up to whatever application's creating that data as far as whether it wants to create a really small Ethernet frame or the maximum size Ethernet frame. Well, what the heck does that have to do with this? Well, every type of network out there, whether it be wired Ethernet, Wi-Fi, or a variety of other things, they all have this maximum transmission unit. Now they're not all the same. Some networks might have a maximum transmission unit of 15, 18 bytes, but others might have 1,000 bytes. Others might have 3,000 bytes. Now, the only thing my laptop knows is the network I'm actually connected to right now. That's the only MTU I'm aware of. So let's say, for the purposes of argument, that I sent out, so let's say this is me right here, and I send out this way a packet, I should say a frame, because now this is not only the IP packet, but it's also the Ethernet headers. That is 1,500 bytes. I was able to create the largest thing. All right, now that gets to my router. Now let's say my router decides, oh, he needs to send it out this direction. But here's a problem. This particular interface is a different kind of network. We're just making this up here, but it could be a different kind of network. And whatever that network is, it doesn't support 1,500 bytes. The MTU on there, let's come up with some number like 500 bytes. All right, well, what's this router going to do? Because he can't take this thing right here that's 1,500 bytes long and put it on that outgoing cable. It's too big. Well, the designers of IPv4 came up with a solution for that. They said, okay, let's take that packet and fragment it. Let's cut it up into little pieces with each piece that will fit on that wire. So here are our fragments. In this case, each fragment could be 500 bytes long. All right, now how are we going to create these things? Because after all, when it finally gets to the receiver, wherever the receiver is that receives these, he's going to need to know a couple of things. Number one, he's going to need to know that all of these are actually fragments of one big packet. So he's going to need to be able to have some way of recombining them back into the original IP packet. Not only that, but when it comes to packet forwarding in a packet network, every IP packet is routed uniquely and independently, which means that if I'm a router, let's say a bunch of packets hits me on the back of the head, all going to the same destination. I just get a bam, 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 a whole bunch of packets all going to 1.1.1.1. Well, maybe right now, at this moment, I say, oh, this is the interface I'm going to use to get to 1.1.1.1. So I start sending packets out this way. All of a sudden, maybe that interface goes down, or my routing table changes. I say, oh, now 1.1.1 is reachable via this way. Now I'm going to send my packets this way. The point is, as packets go through a routed network, they might not always take the exact same path from source to destination. They could take different paths, which means they might be sent out of order. Just because I as the source send them as packet 1, 2, 3, 4, 5, if they're taking different orders through the network, you as the receiver might get them as ordered 3, 5, 1, 4, 2. That could happen here with these fragments. These fragments might be arriving out of order, so the receiver would also have to know, how do I put them back into the original order again? So here's where these fields come into play. Remember how we saw there was an identification field inside the IP header? So this original packet is going to have some identification, some random number. Let's just say ID 123. Okay, well, when the router decides he's got to fragment this, each one of these fragments is going to be given its own unique IP header. Sort of running out of room here, but you get the idea. This right here. So these are IP headers. So each one of these is going to look like its own standalone packet, but it's not. How can we tell it's not? Well, number one, in the IP headers, normally, if these were all unique independent packets, they would all have different identifications. Their ID numbers would be unique. That's not going to be the case. In this case, each one of them is going to have an ID of 123. So whatever the ID was of the original packet before it was fragmented is going to be put into those headers. So that's one way that the receiver is going to know that, oh, these aren't independent, these are all part of an original packet because they all have the exact same ID. Now, the receiver could make an assumption. He could say, oh, I'm getting duplicate packets. Sometimes that happens. Sometimes, for whatever reason, a packet as it goes into a network will be copied and you might get duplicates of the exact same thing, which would be bad. You'd say, I don't need all these, I only need one of these. So the receiver now, he could be thinking, oh, these are duplicate packets, so we need something else to tell him, no, 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 these are not duplicates, these are parts, these are fragments of a whole. So let's go back to the Wireshark here to take a look at how the receiver answers that question. So right here, we can see in Wireshark, when I open up the flags field, we have something about fragments. So here's how this would work. If I take a packet, so let's say this is my original packet right here, and I cut it up into fragments. Let's say this is fragment number 1. So let's say it was going this way, okay? This is fragment number 1, this is fragment number 2, and this is fragment number 3. Fragments 1 and 2 will have this bit set, the more fragments. I'll just put that in here, more fragments, more fragments. That's basically saying, hey, if you get this, this is number 1, this is a fragment because only a fragment would have the more fragments bit set. And it's saying, guess what? There's more to come. I'm not the only fragment, there's more. Now notice this last one here, number 3, he's not going to have the more fragments bit set. So all of these will have the same ID, 1, 2, 3, you know, that's just the random number of the original packet. And now we can see the first 2 will have more fragments, the third one won't. So if we got them in this order, 1, 2, 3, we could very easily reconstruct it, right? But what if they don't come in that order? All right, so let's say we get them in this order. I'll just say RO for received order. Let's say this one, well, it's going to be kind of complicated if I do that, so let's not worry about that. Let's say that this one came first, this one came second, so this is what you're receiving now, and then you receive this one third. How would you put them back together in the correct order? All right, so let's take a look at the first one you got. All right, the first one you got, you know it's a fragment because the more fragments bit is set. You're good to go. Now, where in the scheme is it? Is this the very first fragment? Is it the 19th fragment? You know, where is this thing? Well, there's another field in here called fragment offset. Fragment offset. So if the fragment offset like this says 0, that means this is the beginning of the packet. There's nothing in front of me. So for example, this third one that you got, his fragment offset will be 0. What we mean by offset here is how far away from the front of the original packet is this fragment? Well, this fragment is the front of the original packet. There's nothing in front of him, so the fragment offset here is 0. Now the next one here, number 2, the fragment offset is actually a representation as far as how far away are you from this point right here. All right, so that's the front of the packet. So if we go backwards, how many bytes away from that backwards are you? So let's say this guy was 501 bytes away. All right, so the first fragment was bytes 1 through 500. This guy is byte 501. That's where he starts. So his fragment offset would be 501. So remember, this is this one here in the middle. That's the one we got first. So if you're the receiver, now you know a bunch of things. You know, number 1, that's a fragment because it has the more fragments bit set. And you know, that's not the very first one because otherwise the fragment offset would be 0. And this is a non-zero number. So this is somewhere in the middle. You also know this is not the last one because the last fragment will not have the more fragments bit set. All right, now we get this, number 2. Aha! Okay, it's got the exact same ID, 123. It's got some fragment offset of, whatever, let's say 1,000. But what's important here is that the more fragments bit is not set. It's zeroed out, which means that's our indicator that that is the last fragment. And then lastly, now we get this third one right here. Okay, well, it's part of the previous fragments we just received because it has the exact same identification number. That's this right here. So in this case, it's 123. It's got the more fragments turned on, and the fragment offset is 0. So now we know this is at the very beginning of the fragment. So that's why, I had to skip the identification for a little bit. So these here, identification, flags, and fragment offset, all of that is only used when a packet is fragmented. And it's really for the benefit of the receiver. So the receiver will know when he gets it how to reorder everything and reconstruct the original packet as it was. So that concludes this video on the IP version 4 header fields. I hope you found it useful.